Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, Vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. Welcome everyone. Today we are going to study a very important topic for semester examinations particularly and competitive examinations. Also asked frequently in Vivas, but students generally face a lot of troubles in understanding this particular topic. We will make you understand the topic, what is critical insulation radius, why and when it is required, and also the derivation of the same. So now let's deal with the problem. So what happens is a fluid is flowing through a cylindrical vessel. In or out, the fluid is flowing, and the inner radius of the vessel through which the fluid is flowing, the pipe through which the fluid is flowing is R1, and the insulation is added so that the heat of the fluid doesn't get lost to the ambience. Insulation of thickness R2 minus R1 is inserted. So the outer surface of the insulation will have a radius of R2, as you can see. So this is my insulation coating. So also it loses some amount of heat first by conduction and then by convection to the atmosphere. Now we need to understand as a matter of fact. Now if I question you that what will be happening if we increase the insulation thickness, now you are very obvious about the thing that obviously with the increase of insulation, since it is not conducting, it is an insulating material, with the increase in the thickness of the insulation, the heat loss will be less and less as we keep on increasing, but that's not correct. Up to a certain point, the heat loss will increase with the increase of insulation, and after that it will tend to decrease. And why is it so? If it would have been a flat plate supposedly, and this would have been a cube supposedly losing some amount of heat from inside to outside, and you would have added an insulation over this cubical surface, and you would have increased the thickness of the insulation, then with the increase of thickness of the insulation there would have been lesser heat loss to the ambience, because the surface area of heat loss is not changing with the increase in the insulation thickness. But here with the increase in the insulation thickness, though it is decreasing the conductive loss, because you see from T1 to T2 it is having a resistance of ln R2 by R1 by 2 pi Lk. So if R2 is increased, that is the radius of insulation is increased, the resistance to the heat flow is increased and conductive heat transfer is decreased. But here no surface area change was occurring due to increase of thickness, but here in the cylindrical vessel, along with the conductive heat transfer, it is also affecting the convective heat transfer, because with the increase in the insulation, it is actually increasing the heat transfer surface area. So the insulation increase, the radius of insulation increase results in two things. First of all, due to a thicker insulation, lower heat loss due to a higher conductive resistance to the flow of heat. But along with that, due to a higher radius, a higher surface area, due to which the heat loses readily by convection. So convective heat transfer resistance, if you see, R2 is in the denominator. So if we increase R2, with the increase, the resistance to conductive heat flow will decrease, but to conductive heat flow will increase, but to convective heat flow it will decrease. So this is my convective and this is for my conductive resistance. And this is my net resistance. As we see, from T1 it drops to T2, and then from T2 to T ambient the heat gets transferred. So it faces two resistances in between. The conductive resistance first, when it loses heat from the fluid to the insulating material, Q net, and no heat is accumulated within the insulation, so the same amount of Q net is lost to the ambient air, which faces a convective resistance while it's lost. So there are two resistances in the way: conductive resistance and convective resistance. More is the conductive resistance, the lesser is the heat loss from the fluid to the insulation. More is the convective resistance, the lesser is the heat loss from the insulation to the atmosphere. So what happens is, if any of this increases, the heat transfer decreases. So if by increase of R2 we increase the conductive resistance but we decrease the convective resistance, so we ultimately get a result that with conductive resistance increase, heat transfer is decreasing, but with same R2 increase we see convective resistance is decreasing, because of which heat transfer is increasing. So R2 increase basically results in conductive resistance increase but convective resistance decrease, due to which there will be a balance that has to be struck. So the graph will be something like this. If we perform the Q net versus R2, that is the insulation radius, we will see first with the increase of insulation radius it will reach to a maximum point after increasing and then it will start depressing. So if we have to actually plant an insulation such that we have to reduce the heat loss by the fluid, we have to keep the R2 much greater than this RC, that is my optimum radius at which the Q lost, that is the heat lost, is maximum. So we need to keep this R2 much greater than RC to maintain an insulation such that there will be no excess heat loss to the atmosphere. So we need to understand what is RC. This is nothing but critical insulation radius at which the heat loss is maximum, and after that it decreases. So as we have already seen that two resistances that I take in here, and if we consider the two resistances together, we get something like this. There is no accumulation of heat within the insulation. Q net is nothing but T ambient minus T fluid. T ambient minus T fluid, that is the temperature of the fluid, is T1, divided by the total resistance, that is my conductive resistance plus my convective resistance. So we see that both of these are dependent and we have to maximize this. So this has to be minimum. To minimize this, we need to differentiate this with respect to R2 so that it attains a value of 0, which means this dR net, dR2 will be equal to 0 for minimum R net and maximum Q net. That is, to maximize the heat flow, the resistance has to be minimized. Though we are increasing the insulation to increase the resistance, but since it is decreasing convective resistance, the net resistance will be maximum at some point of time. It will be resulting to a maximum heat flow, and thereafter the resistance will further increase to minimize the heat flow. So we will have to find out where does this resistance, this total resistance, becomes minimum so that this Q becomes maximized. So to do that, we need to actually differentiate this R net in term with respect to R2. So if we differentiate this R net, that is dR net dR2 is nothing but ddR2 of this, which means 1 by 2 pi LH into minus 1 by R2 square plus ddR2 of this, which is nothing but the constants come out 2 pi LK into 1 by R2 by R1 into 1 by R1. So we now see this R1 and this R1 gets cancelled, and what remains if we take this to this side, considering this as 0 for R net minimum, considering Q net as maximum, we get 1 by 2 pi LH into 1 minus 1 by R2 square. This minus will not be there because we are taking it to this side, is equals to 1 by 2 pi LK into 1 by R2. R2 square cancels, 2 pi L cancels, and we finally get from here R2 is equals to H by K. And this R2 is the R2 corresponding to the minimum R net, that is net resistance, corresponding to the maximum Q net, that is my RC is H by K. So my critical insulation radius at which my net heat flow will be maximized and my net resistance will be minimized is H by K. That is my critical insulation radius. If we keep our R2 greater than RC, then Q will be decreasing. For R2 less than RC, with RC increase, Q will actually increase. So corresponding to this graph, it will be something like this, as I have already shown. Q net to R, this is my RC, till this point, RC is equals to H by K, till this point it will tend to increase with increase of R2, and after that it will tend to decrease. So if we have to stop the heat flow, we need to keep the R2 much greater than H by K, that is much greater than RC, that is my critical insulation radius, so that there the dominating factor will be my conductive heat transfer resistance, and my convective heat transfer resistance will then become a minimizing factor, and it will not affect the total as such. Now if you may question that why are you considering this as minimum, it can be maximum, then also it will be 0. But if we double derivate this, that is d2 R net by dr2, you would see this will be something positive, which means that this R net corresponding is basically a negative quantity. So that is it. So you need to keep R2 much greater than RC, which is equals to H by K, as we have already derived, so that with the increase of R2 further, the Q decreases, because this becomes the dominating factor and not this. Before that point, for R2 less than RC, Q increases with increase in R2, and convective heat transfer resistance is dominating. Here conductive heat transfer resistance is dominating. So that's it for today. If you liked our work, like our channel, subscribe to our page and share it to your friends. Thank you very much.